Ok, donc on est de retour en direct. Vous nous entendez bien, apparemment. Donc on va pouvoir commencer. Très bien. Donc rebonjour à tout le monde et désolé pour ces petits soucis techniques, mais normalement tout est résolu maintenant et vous allez pouvoir écouter 45 minutes de géométrie. Oh, so good morning everybody. I am Xavier Tellier and this is a presentation of my PhD work on the generation of curved surfaces in architecture. This is a work joint with Olivier Bavrel, Laurent Oswirth and Cyril Dutz. The difference is actually tomorrow, but it will be held in private tomorrow at 2 p.m. So you can cross your fingers for me. I will at 2 p.m. I will be presenting to the jury exactly what I'm presenting to you at the moment. Before I start, Luc Emmanuel, who is helping with all the technical issues that we are solving, he actually helped us setting up this. This is a green screen, so that you can see me and my slides on your screen at the same time. And so yeah, as you probably seen, you can put comments in the video. You can comment about technical issues if they happen again, or comments or questions about the technical aspect of the presentation. And these I can try to answer them at the end. So the topic of my work was about curved envelopes in architecture. Curved envelopes allow to design expressive, iconic structures. They give a very large design space to fulfill many of the architectural requirements of a project. They even allow to control the environment inside, like controlling the airflow in the Gherkin Tower. And also we know that building materials are responsible for a significant part of greenhouse gas emissions. So given the current environmental situation, it's urgent that we try to minimize the amount of material we use in our buildings. In this respect, the optimal shape to resist a load is never a straight beam or a flat slab, but a curved one. Curvature is what makes the concrete shell of the knit able to span 230 meters with two shells that are only 6 centimeters thick. Now the main issue with curvature, trying to build a curved structure, is fabrication complexity, which appears at multiple levels in the design and construction phases. For example, here is the detail of a connection node in a steel glass structure. You can see that because all the beams come at different angles, you need very heavy welding that is timely and time-consuming to construct this object. Also, the bulk curvature tend to increase a lot waste, as, for example, trimming all the panels of the greenhouse of the British Museum. Because of their irregular shapes, you end up with a lot of trim waste glass that you cannot use. You get even more waste if you actually need temporary structures to support your shell during the construction phase. Another issue comes from the fact that in a curved structure, usually all the elements are different. And because all the elements are different, that complexifies design, fabrication, and planning on site. Now, having a curved geometry does not necessarily mean that the structure is efficient. If you have an example of a museum in Germany that is curved, but the panels do not work structurally at all, and it's actually the opposite going on. We need a very heavy support structure to resist loads on this very complex shape. So what we are trying to do is to get shapes that are at the same time fabricable with the equipments we have, that are efficient mechanically, and that give us design spaces that are wide enough to fulfill all the other architectural goals in our projects. So the topic of creating surfaces that we can build is called as rationalizing the structure, and it's a topic that is not new. Like even in the antiquity, people were using surfaces of revolution to simplify cutting patterns of stones on domes. More recently, ruled surfaces and hyperbolic paraboloids were used to efficiently fabricate the formwork of concrete shells. Or surfaces of translations were used to fabricate grid shells, so grids of bars that are curved and that act like a shell that you can cover with planar quadrangles. So the research has started addressing the topic of rationalization a couple decades ago. For example, at the Navier laboratory, there has been significant work on elastic grid shells, which are lightweight structures that you can put in place without the need for temporary structures. There has been significant work on envelope rationalization, building with planar panels, for example. A big part of research has focused on funicular structures that can resist the given loads without tension, without flexion, in pure compression, so that you get highly efficient shapes. And you can even use quite poor, quite low-grade, low-carbon materials to design your structure. Also recently, the field of architectural geometry has showed how many methods from computer graphics, from discrete differential geometry, can be applied to solve many of the geometrical problems we face when we try to rationalize a curved structure. Now, in this PhD, we focused on the following question. Given a certain constructive system, for example, let's say we want to build a grid shell, a grid of steel bars covered with planar quadrangles, what shapes are possible? Like not any shape, not any pattern is possible with these details. And then the second question is, how can we explore these possible shapes in an effective and intuitive way, such that we can give designers real-time tools to actually design and construct objects with these surfaces. We're going to focus on highly rationalized systems for which there is no generic solution like brute force optimization that you can apply directly. And this work will be guided by 3 observations, 3 case studies that will raise 3 different questions. By looking first at this small pavilion in the US that is packed with a lot of geometrical tricks that help simplify all the elements of a structure, we will wonder how we can apply the same geometrical rules to much wider family of surfaces, and this will guide us to the exploration of surfaces with planar curvature lines. In a second step, we'll look at soap bubbles to think about how we can naturally combine mechanically efficient shapes and fabricability. This will guide us to the exploration of surfaces with constant mean curvature, CMC, and linear Weingarten surfaces. Finally, by looking at this recent pavilion at École des Ponts, we'll wonder how we can make cladding panels and beams work structurally together and how to help this link using geometry. And this will guide us to the new field of Caravelle meshes. Before we start, we are going to need quite a large set of tools to accomplish this. First, we'll need shell mechanics to think about, to reflect on the efficient shapes. We'll need knowledge about fabrication processes. We'll need surface geometry that gives us many tools to study the geometry of a curved, smooth object. And we'll also use its discrete equivalent, discrete differential geometry that studies discrete equivalents of surfaces like faceted surfaces. And finally, we'll need optimization techniques and methods, numerical methods from computer graphics as a way to explore the design spaces that we have obtained. So let's start our exploration by looking at this little pavilion. It's called the Schubert's Club Band Shell. It's built in St. Paul in Minnesota. It's a structure used for concerts in a park for summer festivals. And there are geometrical tricks that allow to simplify each single component of this structure. For example, looking at panels are quadrangular, so this tends to minimize the waste compared to other like triangular or more complex patterns. And the panels are planar. Like if you take 4 points in space, usually they do not lie in the same plane. And so this simplifies a lot their fabrication. No need for bending or for costly molds. And the beams are planar. It is actually much easier to fabricate, whether in steel or in timber, a planar beam rather than a fully double curved beam. Like you can get this with a much better precision. Even better, they are arcs of circle, a constant radius of curvature. And now if we look at the connectors, how everything is linked together, you can see that there is a neat axis connecting all the layers, and even better, there is a constant distance between the structural layers, such that you can actually use the exact same connection detail at each single node of this structure. So now the way that all these nice properties were obtained together in this structure was by constraining the shape to a portion of torus. It's like they're using the inside portion of a donut. So this shape is nicely suited for this project, but might not be appropriate for other ones. So we might wonder, can we design another shape than a torus while still keeping the same fabrication properties? And to do this, we'll turn to discrete differential geometry. Like if we look at all the properties we are interested in this, the fabrication properties we want, on beams, panels, and connector, we can actually get all the ones on quadrangle, on panels and connectors using the so-called circular meshes, meshes in which each face is inscribed in a circle. Now, if we want on the top to have planar beams, the object we want to look at is actually circular meshes with planar lines, so meshes for which each line is included in a plane. And we see that the last property of having like constant curvature radius will actually come naturally studying these properties. So how can we generate a shape with all these properties at the same time? The go-to solution would be to start from an arbitrary shape and try to apply optimization, like move the vertices iteratively such that we can fulfill all the properties. Unfortunately, this works very badly because this is a highly constrained problem. So if you want to deform a shape to get these properties, you will need to deform it a lot. This will take time and will not be intuitive at all. So we propose a method based on the transition between the discrete geometry of circular meshes and smooth surfaces. Like if you take a circular mesh and make the edge length of each face tends towards 0, such that the mesh is approximating a smooth surface, the mesh will actually approximate the curvature lines of a smooth surface. Yes. So if we are looking at a circular mesh in which the lines are planar, its smooth equivalent is actually a smooth surface with planar curvature lines. Now, not any surface fulfills this property. But, for example, the torus that was used for the Schubert club bone shell does, as its curvature lines are circles. So now that we have identified this family of smooth surfaces, we have we have a wide family. We have access to a bunch of powerful tools to explore the geometry of these surfaces. And in particular, one interesting tool is the Gauss map. And this tool can be understood as follows. If you look at the normal vector of a surface at a point, it's a vector of length 1. So you can describe it by a point on the unit sphere. And as you are moving your points on the surface, the normal vector will move and will describe a curve on the unit sphere. So this curve is called the Gauss map of this curvature line. And the Joachim-Stoll theorem from surface theory tells us that if a curvature line is planar, then this curve on the sphere is necessarily a circle. So now if we look at multiple curvature lines, their Gauss map is a set of circles that necessarily cross at 90 degrees. And there are actually not that many ways to have circles on the sphere that cross at 90 degrees. One example is the decomposition of the sphere in parallels and meridians. But there is actually 1 degree of freedom to get more surfaces, more circle arrangements. You can actually move the north-south axis down and still get circles like parallels and meridians that would converge to these poles and while still intersecting at 90 degrees everywhere. So this has been known for quite a while, but what we realized is that from this geometry you can actually go from a smooth object to a discrete one using the fact that taking orthogonal circles on a sphere, if you look at the intersection point of these objects, they actually define a circular mesh. So we have an object here that already fulfills all the properties that we need in our structure, except they are on a sphere. So how do we go from that structure on the sphere to an actual 3D curved structure? Well, we propose a generation method in which a designer will control two guide curves. We'll draw the normal vector to the initial tangents, propagate it along the so-called bishop frame. We propagate it without torsion along the curve. Each normal vector corresponds to a point on the sphere. We then construct circles passing through orthogonal circles passing through each of these points. This will give us a circular mesh. Then at this point we can use a very powerful tool of discrete differential geometry called parallel transformations. Transformations that conserve the orientation of each edge but that do not modify their orientation. So this transformation keeps all the properties that we need. And as this is a simple geometrical computation step, we can do this quite efficiently. So here is, for example, how the geometry of the Schubert club bond shell could be created from two curves. And you can see that you can interactively modify the position of the geometry of the curves and get a new shape that fulfills this. So doing so, like whatever the shape that you draw with this software, you know that you can actually build it. So you can now focus on other aspects of your projects, like mechanics and all the other architectural requirements. You can do negative curvature, but you can also do positive curvature. And for a set of curves, there is actually 1 degree of freedom to define the shape, which corresponds to how the Gauss map is arranged. So here's, if we change this degree of freedom, we modify this shape like this. So here's a variety of surfaces you can obtain with this method. You can get well-known family of surfaces like Dupin Cyclides or molding surfaces of revolution. And from this circular mesh, you can actually quite simply obtain in an automated fashion all the structural details of your structure, like for example to do a multiple layer with quadrangles, with standard details, with all the properties that we described before. Okay, so this was about the study of surfaces with planar curvature lines. Now the next stop of our trip will get us to soap bubbles, and we'll wonder how we can naturally use their structural efficiency to design a curved structure. So soap films are particularly interesting on a mechanical point of view because they're able to resist a uniform pressure with constant isotropic stresses. That means that there is no stress concentration anywhere on any of these surfaces. And these surfaces are very well known geometrically. Like we know that their mean curvature is constant everywhere. This mean curvature is 0 in the case of minimal surfaces. It is a constant that is not 0 in the case of constant mean curvature surfaces. They always give harmonious shapes, and their generation is intuitive as you can control them for their boundaries exactly as you would control a soap film between your fingers, and as you could just like blow on one side to inflate it more or less. So for example, here is a little replica of the boundary of the Great Roof of the British Museum. You can see that the shape we get with a soap bubble is relatively interesting and not that far from the actual shape that was built. So now, how can we use the very efficient shapes of soap films to get something we can construct? Well, the first solution was proposed for the Olympic Stadium in Munich, designed by Frei Otto, in which the geometry is based on minimal surfaces, which are then rationalized by like constructing them as cable nets. But if the mean curvature is not 0, there is at the moment no method to use all these nice mechanical properties. But in the world of discrete differential geometry, there is actually one very interesting geometrical structure called SCMC meshes, introduced by Tim Hoffman. They are like meshes with planar, quadrangles, and sphere packings that can be understood as like facetized, like one very clever way to facetize a surface with constant mean curvature, such that you get a lot of nice properties for the fabrication of a grid shell. In particular, you would get like a very nice simplification of your nodes. You will not have these very complex nodes that we were talking about at the beginning. Like you could define an axis at each node such that all the beams actually meet nicely along it. And even better, you could make sure that you don't have this kind of kink that appears with a property of edge offset. So they have these meshes, SCMC meshes, have a lot of interesting properties, but there is at the moment no available generation method. So how can we construct them? Well, we proposed a method that is again based on the Gauss map of these surfaces. So you remember that for surfaces with planar curvature lines, the Gauss map was based on orthogonal circles. Well, for these surfaces, the Gauss map is best described by a circle packing. And more precisely, it is described by an orthogonal ring pattern, this strange animal here. Circles that are coming in pairs with the smaller circles touching in one direction, the larger circles touching in the other directions, with circles in between crossing at 90 degrees. So the generation method we propose is based on the observation that given such a circle packing, you can build exactly two SCMC meshes. So actually, to build these very complex SCMC meshes, you just need to build the circle packing. And even better, such a circle packing can be built just knowing the radius of each independent circle. So if you know the radius, you can rebuild it entirely, just up to rigid body motion. So to construct this, you just need to solve all the nonlinear geometrical constraints that the radius must fulfill, and you can actually control the boundary of this packing. And the boundary here, you can control you can get it such that it approximates the Gauss map of an actual smooth surface. So doing that, you can approximate the shape of soap bubbles with geometries that you can build as a grid shell. So as we are controlling the Gauss map, you cannot get a very fine control on the position of the final surface, but you can get a very good control on the symmetries of your surface. You can assemble like patches to get into this kind of shape that is like done by assembling three patches together. You can get repetition surfaces. You can repeat up to infinity by just repeating this simple patch in the middle. So that was about SCMC meshes, one way to turn soap bubbles into grid shells. Now if we get back to our soap bubble and we take a bit of altitude, we realize that SCMC mesh surfaces belong to a wider family of surfaces called Linear Weingarten. So what are these strange surfaces? They are defined by this relation. We have a combination of the mean and Gaussian curvature that is constant at each point. So the mean curvature is not constant, it's a combination of mean and Gaussian. And as you would, for example, choose parameter B and C to be 0, you would recover with that relation minimal surfaces. If you choose only B equal to 0, you would recover soap bubbles. But if you chose A and C equal to 0, you get surfaces with 0 Gaussian curvatures, which are actually developable surfaces, the shapes taken by sheets of paper. And by taking other values, you actually get a bunch of surfaces interpolating these well-known families of surfaces. And now, even better, these surfaces also have very similar mechanical properties as soap films. If you apply a uniform pressure on them, like a uniform wind load, these surfaces will be in membrane equilibrium, no flexion, no tension. Even better, the principal stresses will be always aligned with principal curvature directions. So you know that you can, if you are building them as a grid shell, if you put your beams in the principal curvature directions, you'll combine fabrication properties like planar quadrangles, simple nodes, and also mechanical efficiency. And if you choose this parameter C to be equal to 0, you actually get shapes of self-stressed membranes. So despite all these nice properties, again, there is no generation method to construct these surfaces. How can we do this? So this time we are not going to use the gauss map. We are instead going to use the fact that if this relation is fulfilled on the parameters defining this equation, we actually have this relation as an elliptic partial differential equation. That means that you can solve it with Dirichlet boundary conditions. You can find a surface that will fit a closed boundary curve, exactly like a soap film. So inspired from the geometry of smooth linear Weingarten surfaces, we propose a variational definition of discrete Weingarten surfaces, where we will model these surfaces by triangular meshes. And we find them as being the critical points of a combination of the area, the total mean curvature, like the integral of the mean curvature over the entire area of the surface, and the volume. And we show that being a critical point of this is equivalent to say that each vertex of the surface fulfills the equivalent of a linear Weingarten relation, but now in a discrete sense, now combining discrete curvatures in a linear relation. Now, unfortunately, this functional is not convex, so you cannot do just a gradient descent to get to the shapes. So we propose a robust generation method, which is based on the observation that you can actually subclassify elliptical linear Weingarten surfaces into two categories, and this will help you like convexifying your energy and getting a robust generation. We won't tell more about the generation. I'll rather show you how it works for a designer. A designer would basically control a guide curve like this. He would then triangulate it with a triangular mesh. There's a lot of available tools to do this. He would then have 2 degrees of freedom to control the shape, like parameter B and C. Like you could fix A equal to 1. The parameter C would allow you to inflate or deflate the surface exactly as you would inflate a soap bubble. And the parameter B would allow to control the height difference between the saddle points and the mountain tops. So by putting it negative, you would actually get like a much more even crest lines. And by increasing it, you will actually make the structure more expressive by increasing the height difference between the two. So now this tool, you can use it directly to design tensile membranes. If you choose your parameter C equal to 0, you get shapes that are in membranes equilibrium. So if you choose like B to 0, you get a minimal surface, like a well-known surface with isotropic tension. Now by, for example, increasing the value of B, the geometry you would get would actually correspond to increasing the tension in the radial direction of your surface. And if you increase that tension like to the infinity, you actually get to a developable surface. If you choose a value of B that is negative, it would be like increasing the radial tension on your surface, and you will start seeing like this necking appearing near the circles. So we have much more freedom than with minimal surfaces, but we are not able to obtain the shape of all the tensile membranes that are possible on this boundary. For this, you will need to use methods like finite elements, force densities, but this more advanced method would actually require a lot of pre-processing work for a designer. You will need to prescribe the orientation of stresses, the stress ratios, whereas here you can just plug your boundary and obtain a nice variety of shapes. So this is a very useful tool for conceptual design stages in which you are just considering a tensor option but still thinking about other ways to build your structure. Now, as membranes are usually held at their boundaries by cables, well, you can actually include membranes, cables, boundary cables that are compatible with the stress fields of linear Weingarten surfaces. You get that your geometry must fulfill these specific differential equations on the geometry of the boundary, and by using dynamic relaxation on the boundary curves, you can get shapes. Linear Weingarten tensor membranes held by boundaries, cables. For a grid shell, one interesting aspect is that you can create an efficient mechanical shape on even a very complex boundary. Here you have the very complex boundary of the Chatstone grid shell in Australia. And here you can just plug this boundary curve in the software I showed you and directly get to a family of shapes that depends on two variables that will be efficient mechanically. Here's another example on the British a replica of the boundaries of the British Museum. You can see we get this kind of shape in which we discretize this surface along principal curvature lines, such that we have panels that are near planar, we have these nice torsion-free nodes, and we have a highly efficient mechanical structure. And you can observe that this geometry is a bit different from the soap film experiment that we did before. The geometry of the crest is actually much more even, and this is obtained by playing with the parameter B that we showed before, that will play with the height difference between saddle points and hilltops. So now you might say that, okay, it's nice to resist a uniform pressure load, some type of wind loads, but if you have a heavy structures, the vertical loads will be dominant over it. Well, it turns out that if you actually look at this linear Weingarten relation, not using the traditional mean and Gaussian curvature as we define them in our usual Euclidean setting, but in the setting of isotropic geometry. So you have different ways to describe what is the mean and Gaussian curvature of a surface. Then you get to a different family of shapes, and which surprisingly are funicular for a vertical uniform pressure. And this relation is actually not that exotic. If you look at paraboloids, they fulfill this relation. The lesser known pelican surfaces are one particular example. Or again, the surfaces that are height fields of harmonic functions, like the monkey saddle. So now how can we generate this? Well, this problem is actually equivalent to solving the Monge-Ampère equation, which is quite a hot topic in research at the moment. We won't go into details about this, but we propose a new generation method for this based on a geometrical interpretation of this equation. Instead of talking about the resolution, I will rather talk to you about the shape difference between linear Weingarten surfaces and isotropic linear Weingarten ones by looking at the minimal case. You can see we have the same boundary, but drawn with minimal surfaces from the two settings. You can see that if you have a small height difference between your top and bottom boundaries, in that case, you get, in the two case, surfaces that are very similar. But as you increase the height difference between the two, you can see a necking appearing on your minimal surface that is not happening at all in the isotropic case. And if you increase the height even more, well, you cannot actually find the shape of a soap film fitting these boundaries, but you can still find a surface here that really looks like the museum that we were showing before on the pelican surface. So now compared to traditional methods for funicular form finding, again here we have access to funicular shapes in a much smaller design space. We cannot control forces as finely as we would with other methods, but we have a global shape control, which is well suited to to explore shapes quite quickly. And we have the possibility to clad them with planar panels in which your beams will be aligned with principal stress directions, because with these surfaces, if you apply a normal a vertical force, principal stresses are not actually aligned with principal curvature, but they still define a conjugate net such that you can get planar quads easily. Okay, so that was for the exploration of this huge realm of constant mean curvature surfaces and linear Weingarten ones. We shall now turn to our last topic by looking at this recent pavilion at École des Ponts. So this pavilion has a geometry based on an Nexoraid. It's one particular way to assemble beams 2x2 such that you get like very simple connections. One major issue with this type of structure is that it scales very bad. You can do small pavilions with this, but if you try to do a very big structure, a long span, you will have to have very, very massive elements. So to counteract this effect, this structure is a hybrid shell Nexoraid. So the panels act structurally in the structure to resist the loads. And to make panels and beams work together, we had to machine the top surface of the beams such that panels can actually fit nicely on the top surface and that we can screw the two elements together. So if you do not have robots, or if you're working with steel profiles, you cannot use this trick to connect panels to beams. What you actually end up with is a kink angle between your panels and your beams. And this will cause a lot of issues in the detailing if you actually want to connect your beams and your panels. So we propose a solution for this, which consists in moving the curvature away from the edges onto the cladding panels. So basically we propose to fold panels along their diagonals such that beams and panels can have this perfect contact here. So folding panels is actually something that is done quite often for facades. You have a few examples here, even though here these panels are not actually used structurally. So now if you start trying to get a structure that fulfills this geometry, this local geometry here, looking at it at a global scale, you end up with a combination of two meshes on the top of each other. Here in black, you would see a network of beams, as usual, and on the top of this mesh, you would get the fold lines in dashed, like doing a second mesh that is superimposed to it. And you end up with actually two types of connection nodes in your structure. If you look at all the green ones, there is no fold lines coming, so they are planar. If you look at these ones, they're in red, so they're 3D, as in usual structures. And there are actually many ways to combine a fold mesh, like a folding pattern and a structural pattern. Like just by folding quads, you could get into this shape in which we have a fold mesh that is quadrangular. But you could also get into this geometry in which your fold lines define actually a hexagonal mesh. Or you could get this geometry in which the fold lines define a kagome mesh. Here is an example of a shape that would fulfill all these properties altogether. You can also use other types of patterns like hexagonal panels, combining hexagons and quads. And for the rest of the presentation, we will actually use this pattern, folded hexagonals that we will fold 3 times, as we will see that we can then ask much more to the geometry than just this planar, this perfect contact between beams and panels. In particular, we can recover the property of having torsion-free nodes, those nodes with a very neat axis that connects, along which all the beam planes come. And interestingly, if you look at a planar node here, you would have the axis that is necessarily orthogonal to the face under, as the beam midplanes are necessarily orthogonal to the panels above to guarantee that you have this perfect connection between panels and beams. And so doing with this geometry, you would get a configuration in which your face normals in green are coplanar with the vertex normals in red. So you would have coplanar face and vertex normals. By putting these letters together, we get the word Caravelle, which is an invitation to explore the structural possibilities of these meshes for those who believe in curvature. We can also include node repetition. Usually having all the nodes being all the same in a structure is highly constraining if you are using straight beams. For example, if you look at a beam with 4 beams coming together, if you want, this node can be described by 9 parameters. So if you want 2 nodes to be identical on a structure, you will need 9 parameters to be equal. So that is highly constraining. So to get smooth shapes, you will need to relax this repetition of nodes somehow. And for this, we propose the following strategy. We decompose, we use the fact that we have already planar nodes, which are relatively simple to fabricate. And for the 3D nodes, we propose to rationalize them further by optimizing them such that they have 120 degrees in plane angle. We'll see that this allows to get like standard details for this. So now what are the possible shapes with this? Well, again, we turn to the asymptotic case where a mesh is approximating a smooth surface with smaller and smaller edges. We see that in that case, necessarily, the hexagons must be aligned with principal curvature directions to fulfill this property. Based on this observation, we developed in the master's thesis of Mathieu Lerouge a generation method for Caravelle meshes in which a designer would draw a reference surface. We would compute its curvature lines, construct a hexagonal mesh aligned with it, and apply geometrical optimization on it. And as we're already quite close from a good solution, this optimization works very well thanks to its proper initialization. Here is an example of a timber pavilion that we built using these properties. So what's remarkable about this is the low amount of equipment you need to build a curved structures. If you look at the planar nodes, they are made very simply by screwing planks on top and bottom of beams. If you look at 3D nodes, they are built by just taking a hexagonal timber profile. So that's the part that's a little bit more complex to fabricate, but this node here is the exact same for each 3D node in the structure. So you can really use standardization in this detail. And then if you look at all the other beams, you actually just need like a circular saw, and you can cut everything just with one angle. You don't need complex like 2D cuttings to get the beams into shape. Here is another example made of steel and aluminum panels, in which we use these properties to get something that can be built entirely from laser cut elements or with a 3-axis milling systems. The only elements that cannot be built with laser cutting that needs more transformation is this 3D node that is actually like a stamped piece of steel. But for this element, actually, you can just mass produce the nodes as they are all identical throughout the entire structure. Okay. Now, a last application of this is about fast prototyping of curved structure. You can use the fact that you have standard 3D nodes, which are like the most complex part of your system, to get a system in which you have 3D nodes that are 3D printed in advance here, and such that all the other elements are just laser cut, so that you can actually like prototype very fastly a curved envelope using our process. You won't be delayed by the time-consuming part, which is usually 3D printing an element. And we can even add a fourth property to these hexagonal meshes. We can include the property of edge offset. With this property, you can actually put panels on tops and bottom of your beams, such that you can actually get a curved structures with curved sandwich panels. So we can like combine the efficiency of sandwich panels with the efficiency of curvature. For this, you end up with a different geometrical problem, which is much more constrained. We propose a generation method for this also, even though we won't go into the details here. So that's about the map of everything that was explored in this PhD. We looked at surfaces with curvature lines, how we could rationalize all the elements of a grid shell together. We looked at how to combine mechanical efficiency and fabricability with soap films, Weingarten surfaces. We looked at how we can connect structurally panels and beams together with Caravelle meshes. And each of these gives actually a different generation method for a designer. For surfaces with planar curvature lines, you would control those two guide curves as we saw in the video. Whereas for Weingarten surfaces, you would control a closed boundary, like the boundary of an existing atrium, for example. Whereas for Caravelle meshes, you would control actually a surface, so you would have much more design freedom to obtain, to design something. Now, the future work we could think after this would be firstly to explore a bit more on Caravelle meshes. There are many patterns that are available, there are probably many of them filled with good rationalization properties and new structural systems. We could dig further to the use of curved sandwich panels using this geometry. Also, in linear Weingarten surfaces, like explore their full potential in design settings. We could also work at how we can combine these elementary patches of surfaces together with different topology using, for example, recent topology exploration tools. And as time passes, there are always new equipments that come available and new fabrication properties that come that are available, such that new geometrical problems will arise. And in a final note, for a more long-term plan, we can think about how to control a shape beyond just the control of the shape by mouse and screen. And we took using a more experimental physical approach, like is often done by architects. So we took one step in that direction with this little prototype here that replicates mechanically the behavior of a curvature lines parametrization on a surface. So you can actually transform this object only in the shapes in which these are curvature lines, such that you can actually get directly, intuitively a shape with nice properties. So I hope this work has made one step towards making curved structures more accessible because fabricable with available equipments, more accessible because designable by architects or engineers without being the need to be a geometrical expert. The final goal being that we can use all the benefits of curved structures to reduce the amount of materials we put in a building and enjoy their expressiveness. If you want to know more about this topic, the PhD will be out soon. Meanwhile, we have some publications available. And I thank you for your attention. So I will actually take this opportunity to thank everyone who supported me during these 3 years of my PhD. So maybe I'll switch to France, but merci à tous ceux qui m'ont supporté, merci à ma famille, à mes amis qui m'ont supporté pendant que je leur parlais sans arrêt de ma thèse. Donc voilà, normalement si tout va bien, demain j'arrête de vous parler de ma thèse. Je vous parlerai de mon postdoc. Merci à tous les gens du laboratoire Navier. Merci pour avoir fait cet endroit vraiment un excellent environnement pour faire une thèse. Donc merci à toute l'équipe technique qui a permis de rendre nos recherches possibles quand on avait besoin d'aide. Un merci spécial à Marie-Françoise. Merci à tous les chercheurs qui ont pu ouvrir leurs portes quand j'en avais besoin. Ouais. Merci à mon encadrement pour ces 3 super années de recherche ensemble. Et merci à tous les doctorants, bien sûr, pour toute cette chaleureuse atmosphère et toute cette chaleureuse ambiance qu'on a pu avoir au labo. Et enfin, un petit remerciement à toute l'équipe du pavillon de construction de notre pavillon de l'ISS. On a passé 1 an à travailler ensemble sur ce pavillon. C'était un plaisir de travailler tous ensemble avec vous. Donc, c'est la fin de notre présentation. Je vais aller jeter un coup d'œil en régie, voir s'il y a des questions qui sont apparues dans le chat. N'hésitez pas à en poser. Et si oui, j'essaierai d'y répondre. Et sinon, merci pour votre attention.